So what I'm going to do in this video is go through the simulation that you started yesterday and hopefully finished today. I'm sure a lot of you are wondering why we didn't just go through this yesterday, and the main reason is I wanted you to discover a lot of the things that you're supposed to find, not just wait for me to show you. And also, I'm TAing for some online classes at City College, and I notice a big problem a lot of students are having is just simply reading and following directions. I'm sure that when you see a big piece of paper like this with all these words, you want to avoid having to read everything. But if you have that mindset, it's going to stop you from being successful in college. And one of my goals in this class is to get you ready for future academic success. So hopefully you got in the habit of reading procedures and following them. Um, if not, yesterday and today was supposed to be some practice, but now I just want to make sure that you've learned the physics, not just how to be a good student. So step one, we are going to start out with this bending light simulation. Step two, I noticed a lot of you skipped right over this step. You probably just started clicking the first thing that you found, but if you did this intro box, you weren't able to see a lot of the things you were supposed to. So over here on the right, you got to click the More Tools box. Alright, so now what we want to do is check the angles box on the bottom left of the screen, click the red button to turn on the light source, and rotate the cylinder between 0 and 90 degrees from the vertical dashed line. So click the angles box, the red button, and just rotate this and make some observations. So this dotted dashed line, this is sometimes called the normal line. This is the line that forms a 90-degree angle with the surface. So now we've made some observations. Hopefully you're starting to see something that's true about these two angles and something that's also true about these two angles. So jumping back here, compare the angle that the light bounces off of the bottom material to the angle of approach. This angle of approach is sometimes known as the incident angle. It's the angle that the light strikes something at. Notice we're measuring the angle relative to the normal line rather than the angle relative to the surface, but I'm sure you could deduce this using some geometry. So we should see that no matter which angle this light ray is incident upon the surface, the angle that it reflects off it is always equal to the angle of incidence. That right there is the law of reflection. So hopefully your answer to number 5 here, the number 1 on your notes, is not just it does something. You need to tell me what it is. I noticed that on a couple of people's papers yesterday. You have to get out of the habit of writing answers that you cannot study. So using number 13 from your pretest, so let's go down here. Oh, sorry, I thought I had this all ready for you. So number 13, a wave contacting a boundary between two media and all or some bounces back. So media is just the word used to describe the substance the light is traveling through. So some or all bouncing back. You can see in the simulation not all of it is reflecting off of it. So we talked about this in class a little bit yesterday. The light that bounces off of the boundary between two different substances is called reflected, and that's just because the energy in these photons does not match the vibrational frequency of the electrons or atoms in the substance. So it bounces off. Not all of it, some of it does go through. We'll talk about which will go through, which will get reflected, which will be absorbed. That has to do with this stuff. So just jumping back to the simulation, you're supposed to say something here about how the angle of incidence is always equal to the angle of reflection. You're going to have to illustrate this and explain it and label it on your test. So make sure you understand what you're seeing here. The angle that light strikes an object is always equal to the angle that it leaves the object after it's reflected. And it's true about these angles as well as these angles here. Okay, so your next question, how do these angles compare to the angle of the light ray passing through the material in the lower half of the screen? Include number 14 from the pretest to answer. So this light ray right here that's being transmitted, that's going through the material, it doesn't have the same angle relative to the normal line. So this is a 42.1 degree angle, this is a 26.5 degree angle. So this light ray is being bent when it crosses through this boundary. This is known as the process of refraction. Refraction is, I guess, one version of transmission. So if you have transmission where the light rays move right along the normal line at a 90 degree angle or 0 degrees relative to the normal line, it goes straight. But when light rays cross into a different medium and they hit that medium at an angle relative to the normal line, they get bent. The reason why they get bent has to do with them slowing down, but we'll get into those details later on. So jumping back to what you're supposed to answer here. How do these angles compare to the angle of the light ray passing through the material? Basically, just want you to know that the angle changes. The angle that the light rays are passing, or that the light rays are traveling relative to the normal line or the surface, changes as it passes into a different medium. And the main thing I need you to know there is that it's because it changes its speed. That's why it changes its direction. It changes its speed because it's interacting with something more often. Notice up here this top surface is air. It's a lot less dense, so it doesn't interact with the particles as much. Whereas when it passes through glass, glass is a lot more dense, so there's much more absorption and re-emission, meaning the light rays are bouncing around with the atoms a whole lot more, which is slowing them down. Changing their speed means they're changing their direction. I think I got a little bit ahead of myself, might have answered some of these upcoming questions. The next one is to pull the speedometer from the right side of the screen into the path of the ray before it strikes the middle boundary line and into the ray path after leaving this line. So this speedometer is measured in units of C. C is the speed of light, or it's how fast light goes when it's not traveling through any medium. So right here, this is 1C. It's actually a little bit, they're probably rounding up. Light doesn't travel at light speed through air. It does travel at light speed through empty space. But it's about 1C, or 300,000 kilometers per second is how fast light travels when it's traveling through a vacuum or empty space. So what you're supposed to see is that when this goes into a different medium, the light is now traveling only about 2/3 the speed of light, 67 or 0.67, 67% the speed of light. And hopefully you see over here, this ratio between 1 and 0.67 is the same ratio as 1.5 and 1. So how much the speed changes really has to do with this index of refraction, which is just a measurement of how much the light will get bent. So the reason why the speed is changing is because the reason why the direction is changing is because the speed is changing. So how to answer this question? Kind of went over number 8. The C in these readings on the speedometer represents the speed of light. Nature's speed limit is 300,000 kilometers per second. So if you multiply anything by C, it's always going to be equal to or less than. So we see that the speed of the light rays as passing into a different material changes. I wouldn't say that it necessarily slows down. I mean, if our light ray was, let's say that we had glass up here and air down here, well, it's not going to change the medium then, but it doesn't necessarily have to slow down. I would just say that it changes. In this case, it is slowing down when it passes into the different medium. And it's just because glass is much more dense, so there's much more interactions. Oh, wrong button. Okay, so the speed of the light rays change as they pass into a different material. So now I want to rotate the light source so it makes an angle less than 45 degrees from the vertical dashed line. So going back to our simulation, this vertical dashed line, right now it's greater than, so less than 45. Let's go with 30. Now pull the intensity meter, which just measures how much light is being bounced off or transmitted through, from the right of the screen, and measure how much of the light leaves the source, how much of it goes through, and how much of it bounces back or gets reflected. Alright, so we should see that 100% of the light is going to be there before any interaction occurs at all. Now down here we see that about 94% of the light is being transmitted or refracted, which means only about 5.84% of the light is being reflected. So how does the intensity of the reflected light compare to that of the refracted light? Sorry. So the reflected versus the refracted. In this case, we see that there is much more light that's being refracted or transmitted, just in the general sense, than there is light that's being reflected. Now that does have to do with this angle right here. When this angle is closer to 0, see right now you're not getting really any reflection. If that angle is less than half of the way to, you're going to see there's more light passing through than there is reflecting off. So now we need to rotate the light source so that it makes more than a 45-degree angle. So let's bring it to 60. Good enough. Alright, so now 82% of the light is being refracted and 17% is being reflected. So how does the reflected light compare after the source is more horizontal than vertical? Well, essentially what I wanted you to see here is that the further the light's angle is from the normal line, or that you could say the greater the angle is, the more light that you're going to have reflected. So you could say as the angle that the light strikes the surface relative to the normal line increases, the amount of reflected light will increase. So the closer I get to this, the more light is going to be bounced off. And it should be obvious, like the angle that is coming in here, it's going to make it much less likely to be refracted and much more likely to be reflected if this angle from the incident or from the normal line is much larger. So, however you word that, that's totally fine. It's the way that I'm saying it might not necessarily be the same way that you wrote it, but just make sure that you understand. As this angle increases, the amount of light that gets reflected increases, which also means the amount of light that gets refracted will decrease. So notice at this point there's more being reflected than there is being refracted. Okay, so what happens to the lower ray angle after the material on the bottom is changed into, oh, I'm sorry, I skipped a step. So repeat step 11. Rotate the light source so it makes an angle less than 45 degrees of the dashed line. So we'll jump back to 30 here. And then put the intensity meter in front of the reflected light and pull the index of refraction bar to the left towards air. What happens to the reflected light's intensity? Okay, so right now we have an intensity of about 5.83. So as I bring this material on the bottom, I don't think I said that. I saw some people struggling with this yesterday. I should have. The index of refraction to the left towards air. I guess I assumed a lot of you would see, oh, this is already all to the left, so it must be this one. So as I bring this to the left, look what happens to the amount of reflected light. It's decreasing. So when my index of refraction goes down, the amount of reflected light goes up. So it's not that I'm getting less well, I am getting less refraction, but I'm also getting less reflection. So this is when the light is going from refraction to just straight transmission. There is no change in this line's path. So what happens to the reflected light's intensity? It goes down. As the index of refraction of a material decreases, the amount of reflected light's intensity is also decreased. This is a direct proportionality. So what happens to the lower ray angle after the material on the bottom is changed into that on top? How does this compare to the angle of the light from the source? So we already covered this, but just to jump back so we can see it again, as I'm decreasing this index of refraction on the bottom or getting it closer to the index of refraction on top, what you see is those two angles get closer together and eventually they become one. So the main thing you're supposed to see from this part is that when light is traveling and it doesn't change its material, right? Its air above and below this line right now doesn't represent the boundary between two materials. It's just a chosen dividing line in space. This light ray continues on in a straight line, and that's something important to understand is light always moves in a straight line unless it interacts with something else. Or it passes through a very strong gravitational field, but we don't need to get into that right now. Okay, so at the very bottom, press the prism button. Here's where it starts to get a little bit funner, or look a little bit more interesting. So we got a lot of materials here. I see a lot of you did some discovery of your own yesterday, and that's totally fine, but hopefully you were learning something, not just wasting time. So we want to, on the upper right side of the screen, click on the mini rays button in the center, and then click on the red button to turn on the light from this source. So, mini rays right here. Click the red button. So now we have multiple light rays coming from this source. The next thing that I'm supposed to do is grab the lens that bends out and is thicker in the middle, up from the box in the bottom, in front of the rays, and observe how the passing rays' directions change. We're going to use 18 and 20 in our pretest to describe how these lenses bend rays. Ooh. Okay, so right here. So what you should see is that as these light rays pass through this lens that is thicker in the center, thinner on the sides, they get bent inwards. So this is an example of refraction with a specific type of lens. And if we go to your pretest, we can see what exactly we're talking about. So when light rays gradually come to a single point in space, they are said to converge. And the word that is used to, the shape that describes lenses or mirrors that curve out and are thicker at their center, that is convex right here. So this right here, this is a convex lens because it bends out. It's the thickest at its center. And these light rays right here converge, meaning they come together at a single point. So your answer for this one should contain those two words. So for number 8 here, you should say something like convex lenses converge light rays. So just trying to memorize that sentence, you're likely to mess it up on your test, but if you actually understand this process, you will be in much better shape. So draw and label the place in space where all of the light rays come together to a point after they pass through the lens. Use number 16 on your pretest to answer this question. Okay, so here's where I want to actually try and use this drawing app. Let's see if I can make this look not too bad. So instead of just drawing the one-sided lens, meaning one side was flat, I'm going to draw a double convex lens because these are the ones you'll be working with in your lab, and these are the ones that you actually see in glasses. So this right here, whoa, didn't mean to do that, is a convex lens. You're going to have to draw a diagram just like this next week. So you have light rays leaving a specific point, moving in a straight line. Actually, let me get rid of that last one. So what happens when they pass through this thick piece of glass is they bend, and they bend inwards. And when they come together, this whole process of the light rays coming together, this is known as convergence. We'll just say these light rays converge. And where they come together, this point right here, this is known as the focal point. So hopefully you have a drawing like this in your notebook already, or you made something on Google Documents. But I am going to be looking for something like this when I grade your simulation, and when I grade your diagram, or Mr. H does, and when I grade your test. You're going to have to draw something just like this. So hopefully this is the first of many. Alright, jumping back to your simulation. At the bottom of the screen, in the center, pull the index of refraction. Wait, did I skip something? Nope. Pull the index of refraction bar to the left towards air and observe how the point you mentioned above changes its position. Alright, so as I decrease the index of refraction, which really says how much these light rays bend, what's going to happen to this focal point? It's getting further away. So what that means is the focal length is increasing. That's the distance from the center of the lens to the point of convergence. Where that point is, how far away it is, that focal length gets larger as the index of refraction gets smaller. So this is fair game for your quiz in terms of different relationships I could ask you about, but just get a new layer here. So I might ask you to draw a graph. What I changed down here, the index of refraction. And what we saw change as a result over here was the focal length. Now, there's a lot of things that could go in the title. Be the thickness of the lens, or the type of light rays that are passing. Right now I want to leave that out, but we did see that as this amount decreased, this focal length increased. So this is an inverse proportionality. This would probably be L right here, and then this we saw is an N. Yeah, so N right here, and then this L to represent length. And then just to make sure in your pretest, what was the specific number it said? Number 16? No, that was that last one. Number 17. So yeah, number 17 on your pretest. From the center of the lens to where the light rays come together, that measures the focal length. Okay, so we're halfway done now. Hopefully you got this far yesterday. At the bottom, in the center, click the drop-down menu for the objects and select water. And then pull the lens that you just used back in the box at the bottom of the screen. Okay, so we're going to change this to water. We're going to bring this back down. Now we're going to bring up a different type of lens. It's almost like the exact opposite of this type. Sounds similar, but it does the exact opposite thing. Okay, so, whoops. So we've already observed how the passing rays directions changed. Now we want to use 19 and 21 on our pretest to describe how these lenses bend light rays. So this lens right here, this is known as a concave lens. The way that I try to remember this is just think about this area right here as like a little cave, like dugout area. So this caves in right here. And what it does to the light rays is it makes them diverge, which is just a fancy way of saying spread apart. Now, I didn't mention this earlier, and I should have, but the reason why these light rays bend this like so, these light rays right here, since they're all hitting it at a different angle, that angle really determines the angle that they bend inwards, and the amount of glass that they travel through is different. The further they get from the outside, they pass through less glass, and the closer they are to the inside, they pass through more glass. So you would think these ones bend more, but since they hit it at a right angle, they bend less. You can probably see it better when you do it like this. And then these ones, the ones in the center, are passing through the least, so they bend the least, and the ones on the outside are passing through the most, so they bend the most. Alright, so that covers 19 and 21, how these lenses bend light rays. So 19 and 21 on your pretest. The word used to describe light rays that gradually spread apart, that's diverge, and lenses or mirrors that curve in thinner at their center, that is concave. So perfect answer for that last question would be concave lenses diverge light rays. Alright, so at the bottom of the screen in the center, pull the index of refraction bar to the right towards glass and observe how the rays you mentioned above change their direction. So if I make this index of refraction greater, hopefully you all know what's going to happen. Those light rays are going to get bent further. So the thicker this glass, which is really what the index of refraction should measure, is the density. As this material gets more dense, these light rays are going to be bent out much more, which is what you should have written for number 29, or number 12, the 12th thing you should have written. All right, pull the lens that you just used back into the bottom at the box of the screen, or at the bottom screen, then click and drag the triangular prism up from the bottom box in front of the light rays. So I'm getting rid of this, bringing this up. This thing gets a little bit difficult to work with, but you can see multiple, this is refraction here, and then it reflects off the inner edge and then refracts again after it leaves out from inside the, I guess right now, whatever is thicker than glass. Alright, now I want to click and rotate the lower right corner of the prism slightly clockwise to make sure that the light ray is passing through the triangular prism and refracts upwards and to the right. So it's a pretty complex instruction to follow. So slightly clockwise, make sure the light's passing through the prism and refracting up and to the right. So this would be clockwise, up and to the right. Oh, it looks pretty good right there. I mean, it doesn't really matter. It could be down and to the left, or down and to the right. Kind of got to know what you're looking for in order to see what it is I wanted you to, which defeats the purpose of discovering it on your own. But let's see what we can see. On the upper right side of the screen, click this button on the far right. Alright, So let's try to get this thing to go up. I mean, you can see it really good right here, but try to move this around a little bit. There you go. All right, so what I'm trying to get you to see right here, this is the process of diffusion. So use number 15 on the pretest to describe what happens after the light rays pass through. So, not diffusion, dispersion. So when light separates into different wavelengths after passing through an object, this is known as dispersion. So that pretty much right there covers what it is I want you to know. But what's really going on here? The light's getting separated into its main primary colors, blue, green, and red. Anything in between that you see is just a mixture of the three. What's happening is the blue light is getting bent the most. You can see that this angle is greatest from the main angle. The red light's getting bent the least. Now what's going on in here, the reason why, is the blue light is interacting the most with the material. It's got the highest energy, so it's kind of bumping into the most atoms or exciting the most electrons in its way through. So I wouldn't say it slows down the most because it all is traveling at the same speed, but it interacts the most, which is why it is getting bent the most. So that's why it spreads out into its separate primary colors, is because of the amount of interaction between each type of wavelength. That's really the main difference between different colors, is the distance between the crests or the frequencies. Those different colors have different amounts of interaction, which leads to these different angles from the main or the source of the light. Okay, moving on. So on the upper right side of the screen, there's a box that controls the color of the light. Oh, I gotta press this one first. Don't skip an instruction. On the upper right side of the screen, press this one ray button furthest to the left. So here we go. And we want to work with the box that controls the color of the light from the source, showing the number in nanometers. So 1 times 10 to the negative 9 meters. We've been working with centimeters, where this is a 2. Millimeters, it's a 3. Micro, 6. Now we're working with nano. That's a 9. So this is the reading of wavelength. We're going to use the sliding bar to determine the range of wavelengths for the colors of visible light. And then draw a diagram of this range with labels of blue, green, and red. So this isn't going to be too difficult. Up here on the high end, the longest wavelength, 700 nanometers, that's red light. Right here in the middle, green light. Let's see, if this is 700, this is 380, so what would be right in between? Let's see, 400, 320, I don't know. Jump ahead. Let's just say about 530. That looks about the center. Maybe 540. So really all I want you to do is make kind of like a dry, this is what you talked about in your do now yesterday. So let me get a new layer here. I'm not going to make it all colorful for you. But the main thing that I wanted you to see was that if I plot all 3 of the colors, blue light, green light, and red light. Actually, that was terrible. Sorry. Let me do that one more time. Try to make it a little bit more obvious. So we see down here the red light, longest wavelengths, which means it has the lowest frequencies, which also means the least amount of energy. This right here, green light, right in between, not the shortest or the longest. So think of it as the one with the medium amount of energy. And then over here, blue light has the shortest wavelengths, the highest frequencies, and the most energy. I mean, if you think about it, it makes sense for it to have the most energy. There's the most change, the most cycles of vibration. And what we're talking about vibrating is the electromagnetic field, which permeates or is filling up all of empty space. Okay, so the last part of the simulation is the easiest. Try to keep it easy at the end here. So we're going to go to this website, click on play, press the RGB bulbs, red, green, and blue, and we have a person here. So we're going to note the three primary colors of light, red, green, and blue. Please don't just write red, green, blue. Write down red, green, and blue are the three primary colors of light, or the three primary colors of light are red, green, and blue. Now we're going to click and slide the red bar up to the top so red light shines bright. Click and slide the green bar up to the top so the green light shines bright. What pigment does the observer see when red and green photons, these are light particles, pass into her, or I should have said their eye. It's not really obvious, I guess, with the long hair. I made an assumption, but I should not have. So, red and green right here. What do we get? Yellow. So you actually have some color equations that you're going to have to know. This will be the easiest math that you have to remember for the quiz. But I do need you to know that when you combine red light with green light, you get something that's not really called, you could call it secondary color, but it's also known as a pigment. For now, let's just think about it as a color. These are the ones that you already know. There are some new technical vocab words. All right, so pull the green bar back down to the bottom and pull the blue light back up to the maximum. So bring the green down, just red light. That's why this person is only seeing red. Bring the blue up, combination of the two. This color right here is known as magenta. So when you combine red light with blue light, you get a secondary color known as magenta. So that's our next color equation. Red plus blue equals, and I'll write this word out. Some of you may not know this one. Actually, I'll write all these ones out, but hopefully you remember red, green, and blue. Okay, next step. Pull the red bar back down to the bottom, pull the green light back up to the maximum. What pigment or secondary color does the observer see when green and blue photons go into her eye? So this is a word that I didn't know until I was taking/teaching this class. But when you combine blue light with green light, this color right here, I'm sure a lot of you think of it as like turquoise or sky blue, but the word that's used is known as cyan. So last color equation, or addition color equation, when you have blue light plus green light, you get cyan. All right, so if I pull the red bar up to the maximum so that all three flashlights are shining, what does the observer see? So when you have all of the three different frequencies or wavelengths of the light sliver of the electromagnetic spectrum, that's when you get white light. So white light is just a combination of all three. So red plus blue plus green equals white. Okay, so what happens if I pull all of the bars so that none of the lights are shining? You take away red, green, and blue, and you have no light. So black is kind of like the opposite of white. White is all of the light, black is none of the light. So something a little bit new to show you. If you could say add the negatives, but I don't know. Let me save this for later maybe. Actually, I want to manipulate these equations for you. Let's see what we're looking at on time. I can't tell how long it's been. Maybe just a half hour. I'm going to do a little something else. This isn't part of your simulation, but this is something that you're going to be tested on. I want to work with each one of these equations individually very quickly on the next slide. So this covers how you're supposed to earn all the points, but that's just for this assignment, not for your quiz. I want to make sure that when you get introduced to this other stuff, it's not for the first time. So let's start with the last one that you were working with, or the first one we were working with on the last page. Red plus green equals yellow. So we can actually manipulate these equations and say yellow minus green equals, oops, or let's actually say red equals yellow minus green. So this is just a simple example. The main one that I want you to work with is the, I wouldn't say the big one, but the one that contains all of them. Blue plus green plus red. So if you think about what is red light, it's just light that doesn't contain blue and green. If you subtract blue and green from white, all you're left with is red. So that's what red is. It's when you just take pure white light and you pull blue and green out of it. So how does this relate to pigments instead of secondary colors? Let me delete this layer and then where is it? Here we go. So if you look at what is cyan, it's just blue and green. So what am I missing? Red. What is magenta? It's just blue and red. What am I missing? Green. What's yellow? It's green and red. What am I missing? Blue. So I want to, on the other side of this equation, let's forget about this side right now. Let's write what these secondary colors are, or pigments are. Yellow is just going to be white light subtracted by, what am I missing over here? Blue. So if you have something that's yellow, like you look at something that's yellow, what's going on is all the white light that hits it, it's absorbing energy that is vibrating in the blue frequency, or any wavelengths that are blue, the shortest wavelengths get absorbed by it. If you look at something that's magenta, white light is striking it, and the energy or the wavelengths that are being absorbed by it are going to be energy vibrating in the green part of the electromagnetic spectrum. And lastly, for cyan, something looks cyan to you. White light is striking it, and what's being pulled or absorbed by that material is red. So these are the three color subtraction equations. You're actually going to have to know all 6 of these right here. You're going to have to know the color addition equations, right there, here. And you're going to have to know the color subtraction equations right here. Now, if you know this one, you can pretty much deduce all of these. Because if I take white, if I take green away from white, I'm just left with red and blue, which equals magenta. So these kind of form out of logic. If you have these ones and this one, you'll be all right. Okay, so hopefully that helped you understand the stuff that you learned about yesterday and today, and you'll be more prepared for your quiz. Have a good day.